In this video, we're going to be talking about functions. We've already seen a few functions, and we've called them, but the idea behind this module is about creating our own, and it's a very fundamental part of pretty much any programming language. And we're going to close this module with a discussion about its advantages, but just as a little bit of a preview, it's going to allow us to organize our source code much better, because what you're going to see is that when you start to develop real programs after you've learned the full language, your programs are going to be very large, thousands, hundreds of tens of thousands of lines of code, probably not hundreds of thousands. As your code grows, organization of your code, maintainability of your code, readability of your code becomes probably the biggest challenge. It's not so much knowing the syntax. And functions are one of the primary ways, it's not the only way, but it's one of the primary ways and the first way that we're seeing that can, when done right, can greatly or dramatically increase the readability and maintainability of your code. So it's a very important part of the language from a syntax point of view, but it's also very important in terms of the design of your programs. So as you continue through this course, you want to be consistently thinking about, well, how can I use functions to make my code a little bit more readable and workable? Okay, so as I mentioned, we've already seen functions, right? And I'm not sure if we've actually seen the absolute value in the modules themselves, but I know the textbook at this point, we're in chapter, I guess we're in chapter 5 now. I certainly talked a little bit about some of these mathematical functions. So writing the absolute value of a minus b will return back to us. This function will return um, the absolute value of a minus b. And if we were to say, what's the absolute value of x, we can certainly write code to do that. We don't really need to call. I mean, this code would return back to us the absolute value of x. The ABS function is already provided for us, so we don't really need to write it ourselves, but it's there, it's in Python. Same thing with max, right? Maximum will return the maximum value between y and z. We've seen the length function, len, right? So we could do z equals len hello, and we know that that goes through and it counts how many actual values are within that sequence. It would return back to us 5. Print is another function, right? So print actually does a job. It doesn't really return anything. So notice how these functions and length were on the right-hand side of an assignment operator. And that's because they return a piece of information back to us. They produce a result, and we're going to store it in a variable so we can use it later. Print's a function, and it's called the same way, but it doesn't appear on the right-hand side of an assignment statement because it's not actually returning data. It's simply doing a job. It's printing something out. So when a function is called, it may return an object, it may return a variable that represents the result of the code executed. Like I said, it doesn't have to return it, but if it does return something, it only returns one thing. You can't return multiple things from the same function. I put a little star by that because as we start looking at classes in a few modules from now, that won't be entirely true because we'll be able to return objects that contain multiple things, but that's kind of a subtle argument. From a syntactical point of view, function returns one single item. When on the right-hand side of an assignment statement, the return value gets placed into the variable on the left. Right? So this function called f, when I call this with a parameter, right, the parameter y, code will execute. Whatever code that's within f will execute, and whatever it returns will get assigned into the x variable. So knowing how to call functions is very important. We can use the built-in functions of the Python language, but more importantly, we can write our own. And certainly, I don't think writing our own absolute value function is necessarily a good use of our time. Or certainly, if the function exists already, we can use it. But it's good for illustrating how we would do this. Right. So somewhere in our code, we could define a function. So let's call it myABS instead of ABS for absolute value. The first part that we see is there's a keyword. We're defining something. We're defining a new function. It's a new part of the language that we can now use later on after we're done defining it. So def is a keyword followed by the function name that we're inventing, right? And so again, right now we're calling it myABS to differentiate between the absolute value function contained in Python. So the function name follows the same rules as variables, so no spaces. Function names can't start with numbers, but otherwise pretty much anything goes. Parameters can be sent in. So we know that when we call the length function, we call the print function, the absolute value, the max function, all of those functions took something in their parameters. Another good example of this is range, right? Range took 3 parameters, and there were some optional parameters there as well. So our parameter list will be defined between these parentheses. In this case, the absolute value only takes 1 parameter, and it's followed by a colon. The colon represents the beginning of a code block, and everything inside this function, just like an if statement, a while loop, a for loop, is going to be indented by 1 tab or a few spaces. Inside the function, you might have several returns. So for instance, here we have a branch. We're saying if it's negative, flip it to positive, right? So if x is negative, we're going to return the negative of the negative, right? Return the positive value. Or we're going to return just the regular value. If it's positive, just return it. So we have 2 return statements, but what's key here is that only one will execute, and it's not necessarily only because of the if statement. As soon as we hit a return statement, the flow of control returns back to whatever code called this function. And again, to call this function, if we kind of tab over here, I would just say something like ABS of 9, right? Or ABS of P, or ABS of anything, right? P plus 3. Oops, that doesn't really work well for me. Can't get that to stay on the same line, but you hopefully get the idea. So if I called the function like this, my p plus 3 would get evaluated. I don't know what value that is because I don't know what p is. And that'll get sent into x. And then we'll execute the function. And as soon as we return that value, that'll get placed into y. So let's use an example again. So Python has its own built-in square root function, but we've seen, especially through the textbook, some alternative ways and ways that Python actually probably does execute or figure out what the square root of a particular number is. So we've seen several different mechanisms for this, but let's take the best technique, the Newton-Raphson technique, and actually create our own function that calculates the square root of x. And we'll accept a second parameter called epsilon, which is the amount of error tolerance. So if we get the square root of x, as long as the return value when it's squared is within this value, within this window of values, then we're okay with it. That's an acceptable solution for us. So right off the bat, if you don't remember what Newton-Raphson is, that's really not a problem if you're using this function, right? And so this is the first time I'm using the word abstraction, but I'll come back to this later on. This function, when we call it, the caller of this function is just going to say, I want the square root. They'll pass in x, they'll pass in epsilon, but they don't necessarily need to know how Newton-Raphson works. When we write the function ourselves, we do need to know that. But this idea of not worrying about the details, being able to use functions as sort of these blocks that we don't really need to look inside, we don't need to remember all the details, right? We only need to write the details that one time, the first time we write the function, but we can use it over and over and over again and still take advantage of that code without actually remembering all of the details of the algorithm. Okay, so just so we can remember what this was, I copied this out of I just put this on Sketchpad so we can annotate it if we need to. The Newton-Raphson method will calculate the square root of x given a variable epsilon, which is the allowable error. And so the answer to this will be y, and y is going to be initialized to half of x, right? And that's just kind of a wild guess. Right? So we can start thinking of in our code, we'll probably have a variable that'll be initialized to some number. X divided by 2, x will be our parameter, right? And we're going to wait until y squared, right, our guess squared, is within epsilon of x. And when I say wait, well, we're going to be active in this. We're going to continually assign or reassign y to be a next guess. So we want to kind of think of this as the next guess. Okay, And we're using, you know, this formula here to calculate a new guess of y, and that should converge to the solution fairly quickly. So, you know, obviously we don't have a keyword until in Python. We've got one in Ruby, but not in Python. We'll have to convert this into a while loop, but you can kind of see that, you know, here's your loop. Here's your init. And this is actually our stop condition. And eventually I'm going to return y, all right, as the answer. Okay, so let's start coding this up. So the first thing I'm going to do is ask the user for a value. So I'll get x from the user. This doesn't need to actually be an integer, so I'll parse it to a float. And again, I'm not gonna implement the solution right inside my main program. I'm gonna call a function. It doesn't exist yet, but I'm gonna call it square root of x, and I'm gonna put the epsilon value. All right. So again, we're looking at this program as if we already have this function. So if we go to run this, it should not come as much of a surprise. If I enter 9, I'll clean up that prompt message. I get an error because it says square root's not defined. And of course it isn't, right? Because we haven't written that actual function. We need to define that. So let's go back over here and let's define it. Now the rule is you must declare the function before you actually use it. All right, so it has to be above where you start to call square root. So I'm going to start by saying def square root, and we'll put in a number x. And you know, I'm using the same variable here for the first parameter x. It does not necessarily need to be the same value, right? So this could be, you know, user input, right? And we could say user input, square root of user input, and the square root of your input is y. And notice that I don't have to go change user input over here, right? This is a parameter name, and when I call the function, whatever I put in as the first parameter gets copied into the first parameter of the function that I'm writing. Right? And that's really key. The names don't have to match up, right? It's the position of the parameter. Okay, so before I even do much here, I'm just going to return 0. Right? So that's kind of a silly answer. I'm going to say whatever you pass in, the answer is 0. But at least it'll allow me to run a program and make sure that works, or that I don't have any other bad errors. So I'll type in 9 now. So the square root of your input is 0. Okay, all right. So we know that's not the right answer, but at least we can see that you know, certainly square root's returning a value. I can print out y, and things are working. Okay, so let's go back to the notes here, and we have an initial guess of y equals x divided by 2. So let's change this. And again, let's even put answer equals x divided by 2. The fact that it's written as y it doesn't have anything to do with the y down here. Now let's go look at the loop. So until y squared is within epsilon of x, keep going, keep doing this. So we need to reverse this, right? Because this is sort of an inverted while loop. So until y squared is within should be rewritten now to say while y squared is outside or more than epsilon. So let's go back, and what I'm just going to say is while answer squared, and I'm going to take the absolute value of this. It's a difference minus x, and this could be initially bigger than x, or it could be less than x. But the point being is that the difference, the absolute value of the difference, is greater than epsilon. Epsilon is our margin of error, our tolerance. All right, so while that's true, I'm going to generate a new guess. So to get that guess, and again, we look back here, answer will be reset to be answer minus the following terms. So see if we can get this all on the same screen here. Okay, so answer equals answer minus, and we'll put the numerator on top, answer squared minus x divided by 2 times answer. Okay, so there's our equation, and let's see how it works. So if we type in 81, whoops, I get none. All right, so how's that happening? All right, why am I getting none? All right, none is a special type for Python. We mentioned it very briefly during one of the first modules. There's Boolean types, there's int types, there's float types, there's string types, there's object types, and then there's just none, which represents none. It represents no answer has been defined, no value has been defined. So why is y equal to none? Well, if I look at y, it's been assigned the return value of square root. All right, so now I spent a lot of time thinking about the algorithm, but notice I never actually returned anything. So if I call a function and I don't return anything, its return value is implicit, it's none. All right, and that's why I've got that. Now the way to handle this, of course, is just to say answer, or to say return answer. And certainly remember that that's after the while loop stops. All right, so let's try it again. 81. Okay, our input is, the square root of our input is 9.0 blah, blah, blah. And by the way, this stuff, we'll learn a little bit more about this when we cover string formatting and numeric formatting. But basically, we're not guaranteed to get exactly 9, even though 9 is exactly the square root of 81. The point is that this value is within epsilon of the square root. It's within our given error tolerance. I specify my error tolerance as 0.0001, and certainly the difference between 9 and this number is within that value. Right, and we can check some other values. Square root of 42, 6.48. That seems roughly right. So I think we're on our way. All right, so let's think a little bit more about the way I called that function. So I had square root, and if I was trying to find the square root of 25, I'd call it with x and epsilon as the first two parameters. That calling convention is called positional function calling, and that's common throughout most programming languages that you'll encounter. Python is not necessarily completely unique, but it's different from a lot of languages that it also offers a different syntax for function calling or parameter definitions, and that's called keyword parameters. So if I know that the parameter names for square root are x and epsilon, I can actually define them, or I can specify them using the assignment operator. So I can say x equals 25, comma epsilon equals 0.001. This is obviously a lot much more shorthand for this notation. But what this notation allows me is some flexibility. So if for whatever reason I'd prefer to put epsilon as the first parameter, I can do that. I can't do 0.01 and then 25. Right? If I use positional parameters and I switch the positions, Python doesn't know this is an error, but what Python assumes this to be is I want to find the square root of 0.001 within 25 units, which is kind of a ridiculous function call. But they're both numbers, so it works. Over here, if I switch the parameter names, since they're named, they've got their keyword definitions, there'll be no confusion. When I go into the function called x will be 25 and epsilon will be 0.001. Those keyword parameters come in handy when it comes to default parameters. Right? So many times there are parameters to a function that are probably rarely used, and it would be nice when we're calling the function to not have to specify it unless we have a real good reason for it. So for instance, when I ask you what the square root of something is, normally we don't say what's the square root of something within, you know, a 10,000th of a unit. 0.001 is a reasonably small error tolerance. It's probably pretty good as a default. When we create our function square root, we can actually specify this. So if I go into my code, I can actually just say epsilon, if it was not specified by the user, is just 0.001. All right? And the nice part about this is now I can type in square root user input. The first parameter will match up with the first parameter over here, and the default value for epsilon will go in. All right, and so that's a nice way of allowing your code that's calling square root, which presumably you're going to call square root many more times than you're going to write it. Makes it a little bit more easy. If for some reason at this point you need it to be super precise, you could specify your own epsilon, and it would override this when you get called. Okay, so you notice that I created a local variable called answer in my square root function. And local variables sort of open up this whole window about scope. All right, so when I say a local variable z, for instance, what I'm saying is that z is only available, it's locally defined within this function called f. And what that means is that nowhere else in the program, nowhere outside of this function called f, can I reference or can I use this actual value z. Doesn't mean I can't have another variable called z, but it means that I can't actually access that variable itself, the actual value within it. And the way a local variable is created within a function is anytime it's used on the left-hand side of an assignment operator. And I'm gonna point out here from the next few slides, if you're coming from the world of C++, Java, C#, JavaScript, pay really close attention to the way local variables work in Python, because it's actually very different than what you might be used to. It kind of works well for beginners. So if you've never been exposed to those languages, that's probably a good thing at this point. If you have, pay very close attention. So let me repeat, a local variable is associated with a function whenever it is used within that function on the left-hand side of an assignment operator. If it appears on the left-hand side of the assignment operator, it is automatically a new local variable. All right, so let's kind of trace through a few of these programs because it's important to be able to follow the way this works. So references to variable name which are not local causes Python to look outside the scope, and outside the scope really means the parent scope. So in this case, we've got some functions, and then we've got the global scope. So this is the whole program, right? So there's things that are defined on the global scope, f, g, x, and then there's things defined potentially within these functions. So let's follow. Right, the first line of code, we've got some function definitions. The first line of code that will actually execute is x equals 3. As soon as we see that x equals 3, x is actually bound to the global scope. There's a variable created called x, and it's assigned to 3. When I call f, I enter into this function, and I reference x. Right, so I'm using x, and because x is not defined within f, I'll look in the global scope and make sure that I find it there. So in this case, I'll print out 3 because it'll refer to the global variable, the whatever is defined in a global scope. After I return from f, if I'm going to reset x to be 3 and I call g, this is actually going to cause an error. And the reason this causes an error is because when I go to print x, all right, that x needs to be resolved. All right, we need to figure out what x is. However, local variables are determined not at runtime, but at sort of, or not when the function is invoked, but when the function is first read by Python. So in this case, g has a variable called x. It appears on the left-hand side of left-hand side of the assignment operator. Therefore, regardless of the fact that there's an x over here, if it is used inside g, it is a local variable. If it is assigned inside a function, it is considered a local variable. So when Python starts to execute your program, it has already decided that x is a local variable of g. Now when we go to invoke g, when we actually execute g and we jump into this function and we call print x, we're going to get an error because x has not been initialized yet. It doesn't have the value 1 yet. Everything runs in order, right, top down. Right? But x is unequivocally a local variable of g. Right? That's kind of an odd thing. G is not The X in global scope is not actually being used. And again, as a reminder, this is where if you're even an expert in C++, you might want to slow down and take a look at this because it's quite different. Let's go through a little bit more involved, but I'd say still simple example of how these variables work. So again, I've gone through and I've defined a function f. I've got a variable x, y, and z, which at the point where I've run line 7 and line 8, and now I'm about to run point 9, z doesn't have a value yet, right? I haven't actually invoked function, so I'm not back yet. I also note that f, this function, is really considered something that's in scope. It's really actually a variable. It's an object. It's code, though. Once we enter into f, there's a new set of variables created. And the book defines this as a stack frame or a call frame. And this is a very important concept. Y and X are used on the left-hand side of an assignment operator. So as soon as we enter into f, new Y variables and a new Y variable and a new X variable is created. That does not destroy the XY that was created in a global scope, right? But it hides it. Any reference to these variables could access this. So the y equals 1 is pretty self-explanatory. The 1 gets put into y. This one's a little more tricky because on the right-hand side, x appears already. Right? And so in this case, Python is smart enough to recognize the fact that x has not been used yet. Right? So x has not been assigned yet. So even though there is a local variable x, we're now assigning it based on an x variable that's outside of the scope. Right? So x will be taken from this 3. 3 plus 1 is equal to 4, and now we've got a local variable x equal to 4. When we call print x equals, or we'll actually print out x equals 4. At this point, we'll return x. So if we keep going down here, right, we see the arrows flowing in, we print it. When we return x, that call frame is completely deleted. Right? It's removed from memory. But the x equals 4, the 4 value that gets returned here, is flowing back in, and as the return value of f of x, it's getting overwritten, or it's getting set into z. When I get back here now, I've got my value 4, and I'll print out 4, 2, and 3. Now let's try an even more complex example. This is going to have a lot more stack calls, so let's try to go a little more slowly. So first off, what's in scope already? All right, so by the time I get to line 17, I've seen f. So f is initialized, or it's defined in a global scope. By the way, these functions have not been actually initialized because I have not invoked f yet. Right? F hasn't been called just yet. I'm right at line 17. I'm about to execute line 17. So since this hasn't been invoked, Python has not processed this yet. So Python is simply knows that there's a function called f. It knows that there's a local variable x whose value is 3. It knows that there's a local variable called z, but it doesn't have a value yet. Okay, so now let's say we call f of x. Right? We enter into this function. At this point, now notice what's been added. Right? New stack frame. G has been defined as code. H has been defined as code. X has been defined as well. Right? Again, the X on the right-hand side is going to correspond to the one from the global scope, right? And it's going to be used to set that value. Right? So we take the 3 from the global scope, we set the local variable X to be 4. When we print, when we use that variable, if there's a local variable already there, we're definitely going to use it. Now we're getting ready to call H. Once we call H, we're going to create yet another stack frame. Right? H has a local variable called Z. Right? It has that. We know that it's not this one because Z is on the left-hand side. Right? To initialize that, we're going to use X. And the question is, well, which X? Right? Well, X is not a local variable of H. So we look outside the scope. The next layer outside the scope is the scope of F. H is defined within f, so we're going to look within f and say, is there a variable called x? Yes, there's a local variable called x. Take that 4, right, and assign it into z. So when I print, I'll print 4. I return back from h and I call g. G defines a local variable called x. It assigns it to ABC. That x has absolutely nothing to do with this x or with that x. I print ABC back, and now I'm going to return G. All right, and it's kind of strange, but I'm actually returning a piece of code. I'm not returning a piece of data. G is code. G is a function right here. So when I return that, this function, the code that exists within that function, has actually now been returned, and Z has taken on its value. Right? So when I get down here, Z is this code. Everything else has been removed. All the memory associated, with F, once it returns, gets removed. And now I print out X, 3. I print out Z, which kind of prints out as a weird thing in Python. If you try to print out the value of a function, Python will print that out. That address won't be the same on your machine, but it'll say function G. That's a memory address where the code actually exists. But now I'm going to call Z. Right, so remember now Z is a function. Z in fact is G. I'll call G as a local variable. I'm creating a brand new local variable, initializing it to ABC. I'm printing it back out again. I would definitely advise you to take some time and go through this section to make sure that you completely understand the way local variables and scoping work in functions. It's something that often can lead to very strange bugs, can leave you a little bit confused. So you want to take some extra time and make sure that you really understand how the scoping of variable names works. The fact is that in your program, you're probably going to have a lot of variables that are actually named the same thing. If you're writing a program about, circles, circle is going to crop up a lot in your program, and the use of the same variable name throughout your program within functions actually can be a very good thing in terms of readability. However, if you're not familiar and not understanding the scoping rules of the language, it can actually prove extremely difficult to understand what's going on. Okay, so I want to get into a little bit more about why functions are good. And I'm going to kind of get into that in a little more subtle way. I'm going to talk about testing because one of the benefits of a function is that it tends to be a little bit easier to write test code for. Testing with more by writing more code. What do I mean by that? Any programmer with experience knows that manually testing code, and what I mean by that is, if we go back to the terminal here, this is manually testing code, typing in 81 and expecting to see 9, typing in 42 and whipping out a calculator and figuring out whether 6.4807 is equal to 42. Right, that's manual testing, typing and interacting with your program to see whether it works. Most programmers that have been doing this for a while know that that's not really a good idea. And first off, we're inherently optimistic. I don't think I have any errors in this small little bit of code, but the reality is that any code that you personally write, your confidence in that code tends to be once, you might be struggling right now, but as you get better at programming, most programmers write some code and they believe it works. You're inherently optimistic that your code works. You're inherently, and we are inherently lazy. Right? We don't really want to go through the trouble of testing all our code. We've probably just really concentrated very hard. We've worked for a long period of time to get our program to work. Motivation for testing every single possible input and really thinking hard about, does my program really work, requires a lot of discipline. And human beings don't have all that much discipline. Some have more than others. And we don't really want to find our errors. Right? If I spend 6 hours writing a program, I'd much prefer not to find errors. Right? I'd run it a couple times. If it looked good, I'd probably say, okay, it works. Don't tell me about it. I don't want to search too hard for my own errors. That's just human nature. And so after a few tests, we typically declare victory. And unfortunately, programs are complicated. Most programs, bigger programs, are very complicated and have a lot of different possible scenarios that if we don't really test thoroughly, we certainly are going to pay for that later. And so what we've learned over 40 years of programming, or 50, 60 years probably of programming, I guess, is that writing more code to actually test the code that we want to write in the first place is usually a better strategy. So experienced programmers actually write test code before they actually write the real code. They write their tests before they're tired. They write their tests before they're running late, and before they're overly confident that the solution, that their code works. Um, Really, these tests sort of represent specifications or expectations. So I want to go back to the square root function. I want to kind of reevaluate what we really did and think about how we could have started by writing some tests first and maybe gotten a little bit more confident that our code worked. So let's go back to the code for a second. We've got user input for our square root function, and that's fine. I'm going a little bit backwards because I've already written this function, but let's actually do a better test. How could we, if we have, x equals 42, um, and y equals the square root of x, how could we actually determine whether square root returned the right value without having to actually read an output screen from the program, maybe whipping out a calculator and multiplying it? Well, we could certainly say if x, let's say absolute value of x minus y squared is greater than some value, maybe epsilon, test failed. And I'll print out the values too. So if I look at that code, that's essentially code that is testing whether or not the returned value of square root, if I square it, is it actually within the error tolerance that I expect? And if it isn't, if it's greater, I'm going to report back that something went wrong. I'll print my outputs, my input and output. If it was okay, then I'm just going to say test passed. In fact, if I run this now, you might argue, well, you still have to look at the screen, and that is true. My test passed, that's good. But I can use functions to further organize this code. I'm going to actually write a new function, test square root, that tests an x and y value. And in fact, I'm going to say input and result. All right, and I'm going to generalize this. I'm going to say result. Oops, sorry. We'll just pass in input. We're going to say result equals square root of the input. Actually, it's probably a bad idea to name any variables input because that's going to collide with their input function for Python. So you know what, I'll just keep it as x. And I'm going to move that code. I called this result. So, and I'm going to call that function a lot. I'm going to actually call that function for I in range, let's say 0 through 1000 with an increment of 0.5. And let's see if this works. All right, so I'm going to try to test the square root with every single I value between 0 and 1000. And notice I'm trying to step with 0.5. I want to try to test this with floats as well as integers. So I'm going to test square root of I. Right? And presumably I should see test passed printing out quite often. So when I run this, notice I do have an error though. It comes back and says, well, float cannot be interpreted as an integer. And it's giving me the line of code where that happened. And it turns out, and I mentioned it in my lecture slides for the range, but ranges only work with integers. They're not floats. So I can't have a step of 0.5. So I could get rid of this problem. I could just change it to 1, but now I don't really have exactly what I wanted. I would only be testing 0, 1, 2, 3, 4, and all that. So instead, what I'm going to do is I'm going to change this to 2000. So I'm going to test the series 0 through 2000. I'm going to step by 1, but I'm going to divide by 2. All right, so my first value will be 0. My second value will be 1 divided by 2.5. The second value will be 2 divided by 2, 1, and then 3 divided by 2. And so I'm kind of cheating a little bit here by generating a range of integers, but throwing in the test values as floating point values. So now if I run it, you'll notice that I got a lot of tests pass, and if I scroll up, I think I can probably, well, that's a lot of scrolling up actually. Maybe I really just don't want to, I only want to find out if something went wrong. I can remove the else clause. So let's run it that way. All right, so what you'll see here now is that I wrote a little, I took a little extra time to write a function that tested the square root function. So it's a useless function unto itself. However, I just went through and I ran in a split second. How long did that actually take to finish, right? A split second. I tested my square root function with every value, skipping 0.5 each time, from 0 to 2000. And I know that every single time I called it, it worked. I'm a heck of a lot more confident that my code worked now than I was when I just tried 81 and I just tried 42. Okay, and that's sort of the lesson to be learned here, because if we write code with loops and we can test a variety of inputs, we can test thousands of inputs in a split second and become much, much more confident that our program works correctly. And that's an important thing going forward. Okay, so let's go back and talk a little bit more. We've seen sort of a subtle way that functions can help us, right? We can test this function with our code very easily by looking at the return result. Let's look a little bit more about why functions add value. First of all is reusability. So the square root function, the absolute value function, most of the functions that we've used so far, we can imagine them using them a lot. And certainly the functions that are already defined with Python in Python are used frequently. But as it turns out, when you start writing larger programs, you're gonna find that there's parts of your code that might actually be usable across different programs. And we're actually going to soon learn how to package these functions up. If you structure them as functions, we can package them up into separate files and we can share them among programs. So even though functions initially feel like you're probably writing more code than you used to, functions are a great way of saving yourself from writing code. Being able to reuse the same function over and over again, not via just copy and paste, but actually just linking them together. Another big value of functions is abstraction. When you're writing the function, of course, you need to deal with Newton-Raphson, right? You need to deal with the internals of the function. But the point is that once you're done writing that, you can share that across your entire program. You can share that with other people. And they can essentially treat your function as a black box. We can put in an input and we get an output back, and we don't really need to worry about the details. This is really, really important, again, because there's only so much that as a human being we can think of at one moment. And so when you start to think about programs that are 10,000 lines long, if you have to think about all 10,000 lines all the time, and you need to think about the details of every level of calls that you make, you'll never complete it. It's just impossible. It's not a matter of skill, it's just beyond the ability of a human being. Breaking your program down into sections. It's sort of like breaking a huge, a book into, when you're writing a book, you're breaking it into chapters and you're breaking it into sort of an outline. Thinking about it at that level. When you break things up into functions, you can work at a higher level, work at a higher level of abstraction. You don't have to worry about the details all the time. You can just call your functions. Then finally, you get this nice property of decomposition. You're able to break your program up into logical chunks. Each one of those logical chunks is probably a lot easier to understand on their own than the whole program itself. But these easily understood and manageable chunks can be fit together. All right, and so we can build out of the functions that we create, we can build much, much more powerful programs. So think reusability, think abstraction, and think decomposition. Functions are the number one way you can organize your code better and become a much, much more productive programmer. You just have to take the time to understand how they work, understand how local variables work and parameters work. It's tricky. It takes time the first time you've seen it, but is very, very well worth the effort to learn them because you'll find that it greatly eases your ability to design your programs.